Right now you are looking at 300 little dots, each one a token, all firing connections at each other in a tangled red web. That is what standard attention does. Every token talks to every other token, and the cost explodes as the sequence grows. This is exactly why long context feels so expensive and slow. Now imagine we replace that mess with a small ring of latent nodes. Tokens only talk to these latents. The latents talk to each other, and then we broadcast the result back. You still keep global context, but the number of attention operations collapses by an order of magnitude, which is the core idea behind multi-latent attention. Transformers keep a hidden notebook called the key value cache. For every token they store its keys and values, so later tokens can attend back to it. On the left, you see the number of tokens growing from a tiny grid to bigger and bigger blocks, and on the right, a simple memory bar climbs toward the top of the GPU. As we push from short prompts to long context, this bar creeps into the red zone and becomes the bottleneck that limits batch size, context length, or model size. That is why you might have a big card but still cannot comfortably serve long conversations. The cache balloons linearly with sequence length, layer after layer, until the GPU gives up. Here we line up three families of attention side by side: standard multi-head attention, multi-query attention, and grouped query attention. In the first panel, every head has its own keys and values, which looks flexible but also heavy in memory. In the second panel, many heads share a single set of keys and values, which trims the cache but throws away some representational power. In the third panel, we group queries so that multiple heads share a smaller number of key value groups, again saving memory, but at the cost of granularity. The X marks across the second and third panels capture the punchline. These tricks do save memory, but they often pay with quality, so we still want something better. Now we introduce the core MLA idea. Instead of storing a huge, tall matrix of keys and values, we compress them into a much smaller set of latent vectors. On the left, the large blue rectangle with a tight grid pattern stands for the original high-dimensional keys and values, and we pulse it to emphasize how large and heavy it is. An arrow pushes that matrix through a compression step, and on the right, we get a much smaller block with a label that hints at a compressed dimension. The key phrase here is low-rank compression. We are not keeping every detailed direction in the original space, only the important ones that can be expressed by a handful of latent directions. The result is that we can still reconstruct useful keys and values downstream, while caching only this slim latent representation. Behind the visuals, MLA keeps the familiar pattern of projecting the hidden state into queries, keys, and values, but it introduces one extra projection into a compressed latent space. On the left, we briefly remind ourselves of standard attention. You project into queries, keys, and values, run attention on the keys and queries, and mix values based on the scores. On the right, we show the MLA version, where we first map hidden states into a smaller latent vector, and then use that latent to generate the effective keys and values for each head. The important part is that only the compressed latent needs to be stored in the cache. The detailed keys and values can be regenerated from it when needed. So from the model's point of view, little changes, but from the hardware's point of view, the cache footprint shrinks dramatically. A natural question is what happens to position encoding when we compress things this aggressively? On the left side of the divider, you see the cached latent vector, labeled as small and position-free, living comfortably in the cache. On the right side, we compute a position-aware query on the fly, by applying the Rotary position encoding to the query path instead of baking it into the cached values. Both the compressed latent and this position-aware query flow into the final attention block, where we recover full position-sensitive outputs. The separation is the key. We keep the cache tiny by storing only compressed content, and we handle positions on demand for each query, so long context still works. Here we assemble a full picture of how a single MLA layer processes information. At the top, incoming hidden states flow into a compression block that produces the latent representation, and we flag that branch as the only thing that gets cached across time. From there, arrows lead into separate projections that generate effective keys and values for each head when queries arrive. In parallel, the query path stays high rank and position aware, feeding fresh query vectors into the same attention block. The diagram makes a clear contrast. One slim cached branch that carries compressed context, and one dynamic branch that computes detailed queries at runtime, both meeting inside the attention operation. Next, we build three simple comparisons side by side: memory usage, latency, and quality. In the memory chart, the bar for standard attention shoots high while the MLA bar stays low, and we annotate a big percentage drop to show how much cache we save. In the speed chart, the MLA bar is shorter, indicating lower latency, which you can trade for longer context or more traffic. Finally, on the quality panel, both methods get green check marks, capturing that MLA was designed to match or slightly improve performance on benchmarks, not to be a lossy approximation. Together, these visuals say the same thing three ways. MLA is lighter on memory, competitive on speed, and does not sacrifice model quality. Let us recap the whole story in 3 beats. First, the problem. The key value cache grows with sequence length, layer by layer, until it hits the memory wall. Second, the solution. Compress keys and values into a lower rank latent space, and regenerate detailed keys and values from that latent when needed. Third, the result. More than 90% reduction in cache size, with no measurable loss in model quality on typical benchmarks. At the bottom, we pull the big percentage figure back on screen one more time as a memory anchor, so you walk away with a concrete number in your head for what MLA buys you. Thanks for staying through this breakdown of multi-latent attention. If this helped clarify how attention and the key value cache behave under the hood, consider subscribing so you do not miss future deep dives on modern transformer tricks.